Bees are not just pretty insects. They are ecosystem engineers. Approximately 3/4 of the world's flowering plants rely on animal pollination to reproduce, and about 1/3 of global crop production depends on pollinators to some extent. A lot of that work is carried out by bees. Without bees, the world's fruits, nuts, many vegetables, and a huge slice of dietary diversity would collapse into far smaller choices. This is not a metaphor. Agricultural yields, nutrition, and the economies of farm communities are tightly coupled to pollinators. That dependence gives bees outsized importance. Protect bees, and you protect food web foundations. Lose them, and ripple effects cascade through nature and markets. A world of species, 20,000 plus bees, counting. Bees isn't a single animal. It's a huge family of forms and lifestyles. Over 20,000 species of bees have been described. Solitary miners, fuzzy bumblebees, tiny sweat bees, carpenter bees that burrow into wood, and the highly social honeybees that build perennial colonies. That diversity matters. Different bees pollinate different flowers at different times in different microclimates. The global tally of bee species means redundancy and specialization. Together, they form a resilient network of pollination services across the planet. This diversity also means conservation cannot be one-size-fits-all. Protecting a single crop's pollinators may help that crop, but maintaining landscape complexity, wildflower corridors, hedgerows, nesting habitats, protects the whole web. The hive as a superorganism, roles, sizes, and social rules. Enter a healthy honeybee colony, and you'll find a city in miniature. At peak season, a hive may hold 30,000 to 80,000 individuals working as a single unit. One queen, the reproductive core. Thousands of female workers who do everything from cleaning to nursing to foraging, and a few hundred drones whose sole job is mating. The colony functions like a single organism, a superorganism, where individual bees are parts performing tasks that keep the whole alive. That superorganism runs on rules, signals, and hormones. Worker bees pass through age-linked task phases, a pattern called temporal polyethism. They emerge and start as hive cleaners and nurse bees, later transition to wax building and guard duties, and finally become foragers that risk the world outside. This temporal division of labor is flexible. If too many foragers are lost, younger bees accelerate their development and take on foraging early. The colony dynamically rewires itself to meet shifting needs. The Waggle dance, a map in movement. One of the most cinematic mysteries of the hive is how a returning forager can tell hundreds of nestmates where a rich patch of flowers lies. The answer is the Waggle dance, a coded choreography discovered and decoded by Carl von Frisch and refined by generations of researchers. On the vertical comb, the forager runs in a figure 8. The angle of the waggle run relative to gravity marks the direction of the food source relative to the sun. The duration of the waggle encodes distance, and the vigor of the dance signals resource quality. Recruits use the dance as a navigation primer, then apply local scent and short-range searching to home in on the goal. It is a language built from motion, compact, efficient, and stunningly accurate for a dark, crowded world. Experimental trackers show waggle-directed recruits often arrive within a few meters of the indicated site after a short search, proving that the dance is not impressionistic. It is a precise, transferable map that fuels foraging efficiency across the landscape. How foraging scales, the incredible workload behind a pound of honey. The numbers are almost industrial. To produce 1 pound, approximately 0.45 kilograms of honey, a colony collectively visits on the order of 2 million flowers. A single worker's life yields only a tiny fraction of a teaspoon of honey. The rest is the product of coordinated thousands of bee effort. Foragers make dozens of trips per day, each trip visiting tens or hundreds of flowers and returning with nectar or pollen, which house bees convert into honey and bee bread to feed future generations. Those 2 million floral visits compress into a staggering, repeated choreography of sunlight, scent, and muscle. When you taste honey, you are tasting the output of a distributed economy that spans millions of miniature labors and a landscape of floral calendars. Defense, sacrifice, and hive immunity. Bees sting primarily to defend the colony, not to hunt. Worker honeybees have barbed stingers that lodge in mammalian skin. The bee's sting apparatus rips free of the abdomen as the bee pulls away, rapidly killing the attacker and the stinging bee alike. That suicidal defense is effective because the released alarm pheromones summon nestmates to the threat. The sacrifice protects the colony at the cost of a few individuals. Queens have smoother stingers and rarely use them. Their role is reproduction, not frontline defense. This self-sacrificial design is one reason social insects succeed. They trade individual lifespans for the colony's persistence. Demos and decisions: how swarms choose new homes. When a colony outgrows its nest, it swarms. Roughly half the workers and the old queen leave to find a new home. Scouts fan out and return to perform dances that advertise candidate cavities. Through a process of collective decision-making, kind of bee democracy, the swarm compares options and reaches a consensus, often within a few hours. The winner gets more enthusiastic recruitment, and the swarm follows the leading scouts to the new site. Studies of this process reveal simple rules that scale to reliable group choices. Multiple independent evaluations, quorum sensing, and positive feedback create robust decisions without central control. That algorithm has inspired robotics and distributed computing because it is fast, fault-tolerant, and elegant. Their evolutionary edge: 130 million years of success and new threats. Bees have existed for over 100 million years, co-evolving with flowering plants into an array of specialized partnerships. That evolutionary history made them extraordinarily successful, but it also built dependencies. Many wild plants rely on specific bee groups. Today, those relationships are stressed by habitat loss, pesticides, pathogens, and climate change. Parasites like the Varroa mite and emerging viral diseases are central drivers of managed colony losses and major concerns for wild pollinators too. Protecting bees means protecting landscapes, limiting harmful chemicals, improving hive health, and, in some cases, innovating targeted biological controls. Varroa, a parasite that changed everything. If you name a single cause for the massive losses in managed honeybee populations over the last 2 decades, it's the parasitic mite Varroa destructor. Varroa feeds on bee brood and adult hemolymph, vectors viruses, and multiplies inside sealed brood cells. A perfect, brutal life cycle that synchronizes with a hive's reproduction. The result has been catastrophic for many commercial apiaries. Recent surveys show annual loss rates of managed colonies in some regions exceeding 50%, a severe economic and ecological shock that beekeepers struggle to contain. Varroa is not the only stressor. Pesticides, habitat loss, nutritional deficits, and viral pathogens combine in a deadly synergy. Honeybees are crucial, but they are only one story. Over 20,000 bee species worldwide provide redundancy and specialization. Wild bees often pollinate crops even more effectively than honeybees. For example, bumblebees in cold weather, and different species flower at different times. Protecting wild bee diversity through landscape-scale conservation makes agricultural pollination more resilient to shocks like Varroa, impacts on managed colonies. Conservation is not charity. It's risk management for food systems. If you want clear, urgent science about the natural systems that feed and protect us and practical steps to help, subscribe to Discovering the Unknown.